Hello guys, welcome back to TechDose, and in this video we will look at find the maximum number of fruits collected, which is from Leetcode number 3363. This is from the dynamic programming topic and it is not for somebody who is beginning to learn dynamic programming. This question is for somebody who already knows how to solve dynamic programming problems, at least the knapsack type problems. Okay, now let's look at the problem statement. There is a game dungeon comprised of n by n rooms arranged in a grid. You are given a 2D array fruits of size n by n, where fruits at ij represents the number of fruits in the room I, j. 3 children will play in the game dungeon with initial positions at the corner rooms 0, 0, 0, n minus 1 and n minus 1, 0. So these are the 3 corners in a given matrix. Okay, the top left, the top right and the bottom left corner. The children will make exactly n-1 moves according to the following rules to reach the room n-1, which is the last cell. That means the bottom right cell is the target cell. And each child can move not more or not less than n-1. They will have to exactly make n-1 moves. The child starting at 0, 0, that means let's call this child 1, must move from their current room ij to one of the rooms at I plus 1, j plus 1, which means diagonally below, or I plus 1, j, that means to the down cell, or I, j plus 1, that means to the right hand side, if the target room exists. That means we cannot go out of bounds. Okay, the child starting at 0, n-1 must move from their current room ij to one of the rooms at I plus 1, j minus 1, that means to the next row and to the previous column. Then I plus 1 j, that means down, and I plus 1 j plus 1, that means to the bottom right, if the target room exists. That means we cannot go out of bounds. The child starting at n-1, 0, that means this third one in the bottom left corner, must move from their current room ij to one of the rooms at I minus 1, j plus 1, that means the top corner. Okay, I, j plus 1, that means being in the same row you can go to the next column, and then I plus 1, j plus 1, that means to the bottom right cell. If the target room exists, that means we cannot go out of bounds. When a child enters a room, they will collect all the fruits there. If 2 or more children enter the same room, only one child will collect the fruits and the room will be emptied after they leave. Return the maximum number of fruits the children can collect from the dungeon. So there are 3 children, C1, C2 and C3, and each of them have to make exactly n-1 moves in order to reach to the target, and whenever they go to the cell, then they can collect the fruits present there, but they can only collect it one time, and if a child has already collected, then nobody else can collect it. Okay, so everybody has to reach to the target cell in n-1 exact moves, and all their directional movements are already mentioned. So following all these rules, we need to return the maximum number of fruits that all the 3 children collectively will be able to collect from the dungeon. Now let's look at the first example here which is given. So in this case, if the first child is present in the top left, then he has to move exactly n-1 moves, right? n-1 move. You will see that this matrix size is 4 by 4. It is always n by n as given in the problem statement. Okay, here it is 4 by 4. If the first child has to move, he cannot make any other choice other than to just move in the diagonal. He cannot do any other choice, because even though he has 3 directional movements allowed, okay, if he do not take the diagonal all the time, then he will be taking more number of moves than the moves allowed. In this case, n value is 4, so the total moves allowed for the C1, that means the first child, is only 3 moves. Okay, so if he takes the diagonal, which is the fastest route to reach to the bottom right cell, then only he will be taking n-1 moves. Other than that, if he takes any other route, it will be taking more number of moves, which do not make sense, right? Which will break the condition. So that is why, even though for C1 you have 3 moves, I will always be taking the diagonal path for it. Okay, so that is the first point to consider. Now let's see the second child. If you see the second child, then if you start moving, okay, it can take n minus 1 moves in the straight path to reach to the last cell. That is one way, but it could have taken any other path as well, and still it would have taken n minus 1 paths to reach to the last cell. So there can be many possible paths for this C2. But if you see it closely, then C2 cannot cross the diagonal, because if it crosses the diagonal or it reaches the diagonal, then in order to come back to the last cell, it will always be taking more than n minus 1 number of hops, or you can say n minus 1 number of steps. It will take more than n minus 1 number of steps, because the diagonal is at a halfway distance. So if it goes halfway up, then it has to come at least halfway down, and so the minimum steps, if it has to touch the diagonal, then it will be n steps in order to touch the diagonal and come back to the last cell. Okay, and since the problem already says that we have to take exactly n minus 1 steps to reach to the last cell, that means starting from this bottom left, you will never be reaching to the diagonal until you reach to the last cell, because the last cell is on the diagonal, right? So this is the only point where you will be touching the diagonal. Otherwise you will never be able to touch the diagonal and come back, because it will take more than n minus 1 number of steps. So our search area for the second child is only the lower part of the diagonal, okay, only the lower part of the diagonal. And also we will not be considering this last cell, because in the problem constraint it was said that if somebody already collected the fruit, then nobody else will be able to collect that. A fruit can only be collected one time, okay? So C1 has already collected all the fruits on the diagonal. So one was already collected by C1. That means C2 will not be able to collect it. So the search area is only this region which I have shown for C2. And even within this region, only half of this region will be accessible, because only 3 directional movements are allowed. So all the top region will not be accessible to C2. Okay. So the accessible area is quite small in the matrix. Now there is another point to note here, which is if you start at a cell, let's say C2 started at this point, and I will say that C2 can reach to 11 in 2 moves via this path. Then it can reach to 11. If it can reach to 11 in 2 moves, then it can reach to 11 via some other path in exactly the same number of moves. If these are the 3 directional movement which is allowed, then if you start at the same position, that means if you look at C2, then it will be able to reach to a cell in the exactly same number of moves. Okay, the moves will not change. Suddenly you cannot say that I will be reaching to 14, 15 and then going to 11 in 3 moves. No, because upside movement is not allowed. So according to the movements which are allowed, when you are reaching to a cell from any of these start points, okay, from any of the start points, then you will be exactly reaching to the cell. If you reach it via a different path, then the number of moves it takes will always be the same. So that has to be kept in mind. Okay, now this is the main diagonal, and for the same reason, if you look at child 3 where 3 directional movements are allowed, then you know that the search space is only the lower half of the diagonal. Okay, and even in that only this region will be accessible. So we have to try all possible path again for this one and try to reach to the last cell in exactly n minus 1 steps, and the last cell again will not be added for the child starting at this 4, because this one would have been already collected by child C1. Okay, so what we will do is we will break down this problem into 3 parts. First we will find out what will be the total fruits collected by C1, which is the addition of the diagonal. Then we will find out by C2 by trying out all possible path within this search space. Okay, and then we will try out all possible paths starting for this C3 in this search space. Okay, so taking all these 3 values, we can add and return as the maximum collected fruit by all the 3 children. That will be my objective. So in this case, if you look at this example, then it is given that we can collect maximum 100 fruits, and the explanation of the path is already mentioned. So you can just go through it. I think it will be clear. I hope the observations are clear in this case, right? So if you look at the fruits dot length and fruits at I dot length, that means both the row and column are same, which is n. The matrix is minimum 2 by 2 size to maximum 10 to the power 3 by 10 to the power 3 size. That means the total elements in the matrix can be 10 to the power of 6. Okay, so if I consider number of rows to be n, then we cannot write an n cube algorithm, because n cube will become 10 to the power of 9, which is beyond your 10 to the power 8 limit. So this will give you TLE. So we need an algorithm at n square runtime or n square log n in the worst case, but not more than that. Okay, because log of 10 to the power 3 base 2 will be equivalent to 10, and 10 to the power 6, which is n square, times log n, which is 10, will be equivalent to 10 to the power 7, which is less than 10 to the power of 8. Okay, so since we know 10 to the power 8 is a standard for 1 second, I need to run it better than 1 second. So n square log n will be fine, or n square will be fine. I should not exceed n square log n. Now, having understood this, let's now look at the observations. Now in this case, I already told you that we have 3 children. On the top left, you have a child at 0 0. So this will only cover the diagonal to reach to n minus 1, because exactly n minus 1 moves are allowed. The top right, which was our child number 3, this was our child number 1. It started at 0 n minus 1. So this only covers the upper half of the main diagonal, and you know that the child C2 on the bottom left will only cover the lower half of the main diagonal. Okay, because we have exact n minus 1 moves, and I have already explained you the reasoning behind it. And you also know that if any child crosses the main diagonal, then he can't reach to n minus 1 comma n minus 1, that means the last cell, in exactly n minus 1 hops. It will take more than n minus 1 hops. Okay, because if you touch the diagonal and come back, then it will take minimum n hops to reach to the last cell, right? If all these observations are clear, you know how we will be solving it. Now let's look at the dry run of our idea on this given matrix of size 5 by 5. So here I have taken 3 children, C1, C2 and C3. Okay, and I will be defining just 2 cases, valid case and invalid case. Whenever you reach to a cell, it can either be a valid cell or an invalid cell. So if you have reached to the last cell 4 comma 4 in this case, which is the last one, the bottom right, then it is valid only if you have exhausted all your moves, because in the problem it was said that we have to use exactly n minus 1 moves. So if you reach earlier or if you reach later, then it will be invalid for sure. Okay, actually it is not possible to reach earlier, because even if you make this call 1 2 3 4, which is the fastest, it will still be n minus 1. So you can take more number of hops, but you will never be able to take less number of hops, right? But we have to exactly take n minus 1 number of hops, which is 4 hops. The invalid case is saying that in this case the number of moves, if it becomes 0 at any cell, that means you reach to a cell and the number of hops becomes 0 there, that means you have exhausted all your moves and you have not reached to the bottom right corner, so it is invalid. Okay, the path is invalid. Or otherwise, if your row is equals to column, that means you are on the diagonal. Okay, and I already explained that you cannot touch or cross the diagonal. If you do that, then it will be impossible to reach to the bottom right corner with n minus 1 moves. You will be taking more moves, right? So immediately you can trim out that DFS call, right? Having understood this, you already know that C1 will only be able to go through the diagonal. So we can just add up the diagonal values and say what will be the C1's collected fruits. It will be the addition of all these values: 2 plus 3 5 plus 2 7 plus 4 11 plus 3 14. Okay, so C1 will be collecting 14 fruits, and all these fruits will be set to 0 after it has been collected. Okay, so let it be there. We will be applying DFS, or you can say recursion, for the C3. So first I will be applying recursion, and then I will be showing you repeating sub problems and try to apply memoization type dynamic programming on top of the DFS. So the solution for C3 and C2 will exactly be the same, only the direction is different. Okay, so for C3 you already know that the search space is going to be this area, and for C2 the search space will be something like this, right? So let me show you the recursion tree diagram for C3 flow. Okay, so for C3 we will be starting at 4 comma 0, and the number of moves that we will be having initially will be 4 moves. Okay, because n value is 5, I have to make n minus 1 moves, which is 4 moves. Now from here you can take any of the 3 directions. Okay, so if you take the top cell, that means the top right, then it will be 3 comma 1, or you could have taken 4 comma 1, or you could have gone out of bound. But I will always have a check before making a DFS call that I should not go out of bound, and so this call will never be made. Okay, now for this level the number of moves that you have is 3. From one level to the other in the DFS call you will be exhausting one move. Okay, so that is how I'm defining it level wise. Now if you are at 3 comma 1, you can make one of these 3 moves. Okay, so if you make a move and go to the diagonal which will be 2 comma 2, then this is invalid and immediately you will be returning infinity value for it. If it is invalid, I will be returning infinity. If it is valid, then I will be returning a 0 value or the fruits that are available there. Okay, so I'll be returning the fruit count there, the sum of the fruit count. Now from 3 comma 1 you could have gone to 3 comma 2, 3 comma 2. Okay, so is this valid? Yes, it is within the lower half of the diagonal and it is completely fine. Or you could have gone to 4 comma 2 and this is also fine, right? It is fine. Here the number of moves allowed are 2. Now if you try to expand this 3 comma 2, 3 comma 2, then from here you can go to 2 comma 3, 2 comma 3. Now you see that 2 comma 3 is across the diagonal, but I have not provided the check for something which crosses the diagonal, because the same DFS function will also work for C2, and that is why I did not make the code complex. Okay, but you can go ahead and make changes to filter out all these calls, but I have not filtered it out. So in this case I will be making call to 2 comma 3, and then you can consider making the call to 3 comma 3, and you know that 3 comma 3 is invalid, so immediately you will be returning infinity for it. And you can also consider making call to 4 comma 3. Okay, so 2 comma 3, you know, it is outside here. The number of moves you have is only 1, so let's expand this 2 comma 3. From 2 comma 3 where you can go? You can go to 1 comma 4, you can go to 2 comma 4, or you can go to 3 comma 4. The number of moves are 0, and since the number of moves are 0 and you have not reached to the last cell which is 4 comma 4, that means all of these cells are invalid and they will all be returning infinity value. So since you got infinity from all the cells, so 2 comma 3 will also be invalid and it will also return infinity. Okay, now 3 comma 3 was already invalid because it was on the diagonal and it will be returning infinity. Now let's see for 4 comma 3, 4 comma 3. Okay, so from here you can move top right to the right or down. So that means from 4 comma 3 you can move to 3 comma 4, you can move to 4 comma 4, or you can move to out of bound index, which will not be made. The call will not be made. So 3 comma 4 will become invalid because you know that the number of moves are 0 and you have not reached to 4 comma 4, which is the target cell. So this will return infinity. 4 comma 4 is the target cell, so this will return 0. Even though the fruit count is 3 here, it is returning 0 because these 3 fruits were already collected by child 1. Okay, child 1. So that's why it is returning 0 here. Now what will this 4 comma 3 return? The 4 comma 3 will try to maximize the number of fruits, but it will not take infinity. Okay, so leaving out infinity, how much is the maximum? Maximum is 0. So at 4 comma 3 what is the fruit count? 2. 2 plus 0 is 2, so this will be returning 2. Now 3 comma 2, what it will return? It will ignore the infinity because those are all invalid. In the finite values it will see that 2 is the maximum, and at 3 comma 2 what is the count of fruit? 2. 2 plus 2 is 4, so this will be returning 4. Now from 3 comma 1 the call will also be made to 4 comma 2. So let's try to expand and solve this 4 comma 2 as well. So from 4 comma 2 you can go in all these 3 directions, right? So from 4 comma 2 you can go to 3 comma 3. You know that 3 comma 3 is invalid because it is on the diagonal, so this will return infinity. And it can go to 4 comma 3, 4 comma 3, and it can go to out of bound, which will not be made. The call will not be made. Now if you look at this sub problem 4 comma 3, it is already repeating. 4 comma 3 is repeating here. Okay, now you might think that okay, how can you say that 4 comma 3 is repeating? Well, I have already explained you beforehand that if a child starts at a point and reaches at a point by certain number of moves, then if he reaches to the same cell via some other path, then it will exactly be the same number of moves according to the 3 directional moves which are allowed. If you follow this rule, then you will be reaching to the same cell from the same starting point via different path in the exact same number of moves. Because why this is happening? Because if you take one move in either of these 3 directions, you are moving forward by one time. Okay, so always you will be moving forward, either up, right, down, right? So that is why the number of moves will not change when you reach to a cell, because of this 3 directional movement, the nature of the movement. Okay, so that is why even though you will be compelled to say that row, column and moves will be the state, or these are the 3 variables on which your answer depends, but I can always cancel out the moves, okay, because of this important observation. And that is why I can say that if I reach to 4 comma 3, then this is a repeating sub problem. So the answer returned here was 2, so you can simply return 2 without having to solve it. And how this will be possible? This will only be possible if you have created another matrix called memoization table of the same size as the matrix 0, 1, 2, 3, 4, of the same size as the matrix. Okay, and all the input values have to be something invalid. So in this case, the fruit collected cannot be negative, so I'll be filling this entire matrix with -1 values. So if I see that 4 comma 3 has a value 2 which is not -1, and if I reach to this point again and I see that okay, it is not -1, then I will be returning that value whatever was already calculated, because I know the result. I don't need to calculate the same sub problem again. Okay, so this is how it will be returning 2. So for 4 comma 2, what this will be returning, it will be seeing infinity, and this was already invalid and it saw only one finite value 2. So at 4 comma 2 the count was 1, so 2 plus 1 will be 3, it will return 3. So at 3 comma 1, here you have an infinite value, ignore that. Out of 4 comma 3, 4 is the maximum, and at 3 comma 1 you have 3 as the fruit count. So max of this 4 comma 3 is 4, 4 plus 3 is 7, so this will return 7. Okay, so this is how the calculation will happen via 3 comma 1. Now let's see how the calculation happens via 4 comma 1. Okay, via 4 comma 1. So since I do not have space here, I will be moving it to the right hand side. Here the number of moves available are 3. At 4 comma 1, you will be making 3 calls. Okay, so one call will be to 3 comma 2. 3 comma 2. One call will be to 4 comma 2. 4 comma 2, and another call will be invalid, so it cannot be made because it would have been out of bound. Now if you look at 3 comma 2, then this was already calculated and it would have returned 4, so this will be returning 4 simply. If you look at 4 comma 2, 4 comma 2 was already calculated, it would have returned 3, so I will be returning 3 here. And so out of these two options, which one is maximum? 4 is maximum. If you look at 4 comma 1, the value is 3. So 4 plus 3 is 7. So this will be returning 7 as well. And now at 4 comma 0, it will be taking the max of 7 comma 7, which is 7, because the other call was invalid. And at 4 comma 0 you have 1. So this value will be 8. So the total collection by C3 is going to be 8. And if you calculate for C2 using the same recursion tree diagram with memoization table, then it is going to be 8 as well. So the total collection will be 30, which is 14 plus 8, 22 plus 8, 30. That will be the total collected number of roots. So I hope this recursion memoization technique was clear. This is good enough for your interviews anyway. And it has a lot of observations, so definitely it is not beginner friendly problem. Now having understood this, the collection made by C1 could be made in order of n time. The collection made by C3 can be made in order of n square time complexity and n square space complexity due to the n square memoization table. Why n square time complexity? Because the total number of sub problem will be n square, which is the size of the table itself, n by n, right? These are all the unique problems. And for C2 as well, the time complexity will be n square. And we will be using the same memoization table, so I will not be using extra space for it. The extra space was already added in C3. So the total time complexity is going to be n plus n square, which is going to be order of n square, and the space complexity will be n square. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the fruits matrix and I will be finding the size of the table. So step 1 is to collect the fruits by just parsing the main diagonal. So this is the first child collection. The second step is to do the second child collection from the top right corner, and I will show you the DFS function, but you know that there were 3 directional movement and I have shown these directions using this direction values. So if you are at, let's say, r comma c, then this 1 comma minus 1 means 1 will be added to r and you will get r plus 1, and minus 1 will be added to c and you get c minus 1. So r plus 1 c minus 1 will be this direction. Okay, similarly for this down direction you will have 1 0, that means 1 will be added to r and it will be r plus 1, 0 will be added to c and it will only be c. So that's how it is the down direction, and similarly you can imagine that it will be r plus 1 comma c plus 1. So this is how we can form the directions from r comma c, and we will be defining a memoization table of n square size, all filled with minus 1 values predefined. Okay, so I will be showing you the DFS function in a while. After collecting the fruits by second child, we will repeat the same process for the third child as well. And here we are resetting the memoization table again to minus 1 to reuse the same space, not to define another table, right? After all the 3 children have collected the fruits, we will be adding and returning them as the maximum number of fruits that can be collected. If you look at the DFS function, where we are using recursion plus memoization, we will be taking the fruits matrix, then the row and column where we are present, the number of moves that we still have to make, then the memoization table and the directions array. Now you already know that if we have reached to the last cell, then we will be checking if the moves are 0, then that means we have successfully reached by making n minus 1 number of moves, and we will be returning 0 because the last cell was already collected by C1. Otherwise, if we have reached there by more number of moves, then we will be returning infinity, which will be invalid path. Okay. If we exhausted all the moves, then also we will be returning infinity, or when we touch the diagonal, then we will be returning infinity because we cannot come back to the last cell in n minus 1 moves. That will not be possible. And if we do not hit any of the base cases, then we will check if this subproblem was already calculated, then we will be returning the value. Otherwise, we will be trying to calculate the maximum fruit collection. Okay, so we will be making all the directional movement by adding the row to delta row and delta column. So finding the new row and new column according to the direction and checking for the boundary case. That means I should not go beyond the boundary. It should be within the boundary of 0 to n for both row and column. Okay. If it is also within the boundary, then I will be making the DFS call to the new row, new column, and I will decrease the number of moves by 1 because we have made one move to reach to the next cell. Okay. And if the value is not equals to infinity, then that means the path must have been valid. And so I will be trying to maximize the fruit collection. Okay. By just using the valid paths. If the value was infinity, then I will not be considering that path altogether. Okay. And finally, I will be returning the maximum fruits. If the maximum fruit somehow is less than 0, that means I could not find any valid path, then I will be storing infinity value at that table space. Otherwise, I will be adding the fruits at the current cell plus the maximum fruits that I could have collected by taking the optimal valid path. So this is the entire DFS function. I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.